Good. Okay. Um, so I wish I could do what the chair has just told you, that I would talk about machine learning applications, but it's still in the future. But what I'll try to talk about is what are we doing, what we are setting up, and what the status is, what we're currently busy with. And yeah, that would be nice. It might stop in the middle of the talk. So okay. So. Yeah, so this is I'm gonna give a status report. Hopefully in a year or so it will be in a better state. And so I'm gonna talk here about faint object detections, and the kind of objects are so-called ultra-diffuse galaxies. And don't worry that the objects, for example, at the bottom are a bit faint on the screen because they're really faint, supposed to be faint. So let's start with the Fornax Deep Survey, a survey that we have obtained in Groningen and in other places in the last 5 years. It's basically given an introduction to what it is. Then talk about the EU network that Rien just mentioned, and then talk about the detection of ultra-diffuse objects. And of course, this can be generalized in terms of detection of all kind of faint objects in other fields, but we're still we're busy with astronomy. Good. Okay. To set the scene, one of the most obvious observational effects when studying galaxy evolution is the fact that galaxies in clusters look different from galaxies outside clusters. The so-called morphology density, that the way a galaxy looks is very much determined by its environment and by how it has interacted with its objects nearby. You see it here, there's a cluster and there's a field. In the cluster you see lots of elliptical shaped objects. In the field, if you look, then you see all kind of galaxies, star forming, non-star forming, etc. And if you then zoom in on a few nearby large galaxy clusters, you see also that they're very different one from the other. So Coma is a very massive cluster, sits full of these blue things which are giant ellipticals, and big red squares which are even more massive ellipticals, and then a few spirals, especially the outer parts. In Virgo you have a situation where still the center is dominated by the ellipticals, but then the spirals are much more farther out. And then Fornax is smaller, however the center is more elliptical dominated again. So there are differences from cluster to cluster, all of them caused by the environment. The idea, then the point is then we want to for dwarf galaxies, for faint galaxies, the effects of the environment are even stronger. And I'm not going to show this because of lack of time, but for dwarf galaxies you need to be able to observe them well. You need deep data. And in recent years, say last 10, 15 years, this is a revolution with detectors, computers, etc., telescopes. It has become possible to go deeper and deeper with the data. And so then you want to observe nearby clusters, because nearby means that you can go deep. Why do you want to go to Fornax? Well, basically Fornax is one of the nearest large clusters. It's not in mass, it's actually only 7 times 10 to the 13th. It's smaller than a few other ones, but it's still a fairly massive cluster. And since it's so nearby, you can look at you can spatially resolve things. The other thing is, well, this actually didn't show, this shows up here, is that this is the cluster, and this is a group of galaxies that's falling in. And if you observe Fornax, you can see, you can investigate the process of the galaxies falling in, and what happens then if stars are being formed, etc., etc. So, given the fact that there was this telescope available for the Dutch community and for the European community, to which our conference organizers, Edwin Valentijn and Koen Kuiken, also contributed heavily, and also the colleagues in Naples, and that telescope had a field of view of 1 square degree, and that for current telescopes is large. Of course, with LSST, it's coming up, it's again becoming small. But remember that since photographic plates, there has been a long period that the fields of view were very small. This is the field, this is the cluster that we observed, and if you see these numbers, it's just, if you're not an astronomer, just think that it's deep, and this is actually a magnitude deeper than KIDS, and another magnitude deeper, and another magnitude deeper than SDSS. So we did this in 4 bands. The cluster, basically, as you compare it with the KIDS survey, which is much larger, it's deeper, and in both cases there's a lot of multi-wavelengths data. So I've mentioned a couple of surveys here, and but there's more, and I'll get to that in a minute as well. This is the group of people that did this most, and the 2 main partners here are NOVA and the University of Groningen and the University of Naples, which then built the telescope. This is a group of people at one of these meetings. And here is a lot of additional complementary data that for a large survey nowadays in astronomy is really needed, because a lot of extra information can be obtained from those data. I'm not going to go in detail. All right. SUNDIAL. So if you want to then, the idea of SUNDIAL was that you want to put a number of astronomers and computer scientists together, as we have in this room basically, to and if you put them together and you give them a large number of a big data set or a number of big data sets, you like them to work together. Having them work together is actually not easy. I mean, as it's obvious in this conference as well, sometimes it works, sometimes it doesn't work, but it's really only working if both of them can do the things that they want to do. So astronomers work on data and on physics. Computer scientists work on algorithms, and they don't work on interpretation of the data usually. Astronomers don't work on algorithms, although sometimes that happens a bit. But I mean, you want to let the people who are specialized in certain things do their specialization. And so in SUNDIAL we have the 2 groups together, and they work on surveys, on the previous surveys, as test data sets for a number of applications. And the final goal is basically to be able to apply those data sets on large missions, future missions like Euclid and LSST. One of the work packages, I mean, so there's a number of topics that we concentrate on. One is the faint object detection that I will talk on in a few minutes. Another one, this is then the work package 4, is that we want to characterize and visualize simulations. If you have seen the Gaia data, I mean, the Gaia data release was in April. It was a huge data set of more than 1 billion sources, and all these sources have positions which then change in time, giving proper motions, brightnesses, magnitudes, etc. And from that you can see streams of objects, and this is the same in simulations. So if you want to know what really a simulation is, you can see movies, but if you want to quantify movies and characterize movies, it's actually not so easy, and people use all kind of tools to quantify features in the simulation. But we thought that in astronomy some more work on that could be useful. People use, for example, things like halo finders. So if you have a halo falling into a cluster or whatever, this is the way to follow what's happening. Well, so there we have astronomers who are interested in this subject. Computer scientists like this because they can optimize their tools to characterize a set of data points. And so we're working together in a couple of nodes in the network. I mean, there were, if in the picture that I showed, there were 8 nodes in this network, and some of these nodes work on this topic. For example, here you have some streams in simulation, and this stream, they evolve, and at some point they become something like that. And so, how do you really want to compare your data with that? If you like to do this in numbers, or you like to somehow tell you how good the comparison is, and so on. So we're trying to use some multi-manifold algorithm comparing, seeing what the dimension of features is, and so on. still a lot of this is still completely in progress. So let's talk about ultra-diffuse galaxies and and detection. So this is an ultra-diffuse galaxy, and as you compare it here to the Sombrero or some fainter galaxies, the surface brightness in the center is something like 7-8 magnitudes fainter, which is 3 orders of magnitude or so. So what is interesting about ultra-diffuse galaxies is that we are discovering more and more, and that we're discovering that the universe consists of many more objects than we thought. And of course, this is exciting, and that's why at the moment is a kind of bandwagon, and many people work on it. So this is the properties generally of ultra-diffuse. There's of course a whole range. About stellar masses are about this amount, 10 to 7, 10 to 8. The sizes, and that's what makes them peculiar, are 1.5 kiloparsec vector radius or more, which is a bit like the Milky Way. So this is why people say we find more Milky Way-like galaxies. There's generally reddish, so not without much star formation, fairly regular, and in clusters basically they're distributed a bit like the rest of the galaxies, except that in the middle there's a lack of them. That's not clear at the moment why. And there's issues about dark matter contents. We don't really know for sure, but there's a couple of indications that they're high dark matter dominated in the center. But since they're so faint, observations are hard, and this is still completely under debate. So what are we doing here? We have the survey, the FDS survey. We're also using a few other surveys like the Stripe 82 deep Sloan survey. We are also going to work a bit on kids using similar techniques. We have computer scientists who have experience in doing this in the past. Here, for example, in Groningen, between Michael Wilkerson and Scott Traeger and Edwin Valentine at that time. We have PhD students in both fields, computer science and astronomy, who work in pairs. That means that the domain knowledge basically is then all the time there. And we have frequent meetings of scientists. And so, well, here you see 2 objects. I mean, here's one, and there's another one, except that you don't see it easily, but it's in the noise pattern. In principle, the noise goes up towards the middle, towards the center of an object. So, so the problem is then, okay, you want to make algorithms, but then you want to say, well, what is the ground truth? What is there? How do we know what the computer should get? And so the first thing we did is that Aku van Hola, a PhD student of mine, went through this 4 square degrees and looked at the plates by himself and spent probably a week or 2 looking at the plates and found, in the end, 204 galaxies that are low surface brightness, and of these there are 9 that are larger than 1.5 kiloparsec, which are basically called UDGs. So there you make basically a sample that should be the sample that the computer algorithms should detect. There might be more actually, so it's not really a ground truth, but it's something which gets close to it. And we also do it in simulations, but of course simulations might be not exactly what we see in the sky. And at the moment we are doing testing of algorithms. So the first one is this extractor algorithm, of course, which is generally used in astronomy by, I would say, 90% of astronomers who find objects. And is also available, very nicely documented and so on. Of course, it's not built for faint object detection. And then there is a tool, the code is Empty Objects by Wilkinson, basically, and which was published in 2016. It's an object where they have several thresholds, and they use all the thresholds to find them, so they're a bit better than Sextractor. They have Deep Scan, which then goes and basically improves the algorithm of Sextractor. Noise Chisel is a genetic algorithm that also tries to faint. It is actually now available in GNU Astro, quite successful. And then there's Profound, which is coming from the Gamma collaboration. So, I mean, you see from the years that this field is really popular and moving and taking off. So we don't have many conclusions yet. I mean, this is from the paper by Arklagi et al. So that he shows that he's much better in his algorithm than Sextractor, and that's not that difficult to do. We find that basically all the algorithms are better than Sextractor, and that none of them is that much, then none of the others is that much better than the others. But it depends on the circumstances and the parameters and how you set it. And so we're doing basically setting up unbiased ways of testing the algorithm. It's very hard because there's lots of parameters that you can tune. But of course, if you have to tune 30 parameters and you only have 10 minutes, how do you do that? So this is, for example, a test between noise chisel and empty objects here. And so this is the image on a certain scale. Noise chisel is being run. This is the segmentation map, or this is the objects that are being the pixels basically that are being found. This is the forget about this one. This is the segmentation maps from empty object, where you see the different objects. This is what the things belongs together, and so on. And then here are the objects in green that are being found with the two methods, and we are comparing all of them with each other. And if you look here in the zoomed version, you see them. And of course, you have to see whether the objects that are I'm done basically. That the objects that are being found make sense, how big they are. I mean, this is about detection. Then the next thing is parameters, of course, because once you have a detection, it's not sure that the parameters that it gets are reasonable. If at the moment, the parameters that empty objects gives don't make too much sense, but the detections themselves make much more sense. So we're basically in this process, and hopefully within a year or so there should be a lot more information. We should have better algorithms. At least they're doing a lot better nowadays than Sextractor. So what to take home? SUNDIAL is an interdisciplinary collaboration. Is the aim of developing new techniques to analyze large amounts of data. We're optimizing detection of faint objects using deep data sets, and we hope to able to use the expertise that we built here in other nearby fields. Thank you very much.
Question here to sound the box.
The box. Box. Someone took it home.
Well, yes, try. Pretty damn good.
No.
And for your faint galaxy detection, is any of the algorithm that you mentioned, does it include deep learning? Because that would be an interesting thing to try, especially if you have a good set of labeled examples.
I think in noise chisel some of this can be implemented, but not really very well tested, for example. No, or that would be so. The aim is actually, once you have done this, then is actually what we're planning with a group in France, in Paris, to start looking at doing things in that direction. Yeah.
More questions? So except for the results in terms of techniques developed, what is the goal in the end, physically speaking, with respect to the galaxies? What question do you want to answer?
Well, first of all, you want to find them. Then you want to say, what is their distribution? Do you is this lack of that lack of objects in the middle of clusters? Is it real? If it's real, then presumably there is a lack because they get destroyed in interaction with other galaxies. Are they as abundant, for example, in the outer part of clusters, the inner part of clusters? So that do they have anything to do with clusters? So yeah.
Yes? Any more questions? May I then thank the speaker again? Thank you, Reynier.